Okay, so this is 16.5, cylindrical and spherical coordinates. We'll start with cylindrical. The idea here is very, very simple. We've got, in two variables, we have r and theta, r representing distance from the origin, theta representing the angle from the positive x-axis. If you want to work in space, which is what cylindrical coordinates is going to allow us to do, you can just extend into the z direction by adding the z variable. All right, so cylindrical coordinates are going to be coordinates describing points in space using r and theta as your kind of position in terms of the xy position. Or another way to say it is perhaps your shadow on the xy plane of your point in space is going to be described using r and theta, and then you just add z for the height. All right. Okay, so these are, because polar coordinates are well suited for working with circles, right? This circle right here of radius 3 is easily described as just r equals 3, right? Cylindrical coordinates are very well suited to describing cylinders. So x, y, z, cylinders about the origin, pulled outwards towards the z direction, more precisely. So if this is a circle of radius 3 here, and I pull it out as a cylinder, right? So in other words, x squared plus y squared equals 9 in space, right? Then this is super easy to describe in cylindrical coordinates. It's just, well, x squared plus y squared converts to r squared. So r squared is equal to 9, and so r is equal to 3. All right. Okay. So we're interested in integration. How do you integrate? Well, since all we're doing is we're just adding the z direction, integrals are going to be just like we did with polar, where you have to integrate and then r d theta. But because we're just adding the z direction, just a dz. All right. So in terms of the concepts, it's relatively straightforward, a relatively straightforward extension. Let's do an example. So let's find the volume of the solid that lies below the plane x plus 2y plus 3z equals 6, above the xy plane, and within the cylinder x squared plus y squared equals 1. Okay. So in a picture, this would be something like we've got a cylinder, we're cutting it with a plane. It's tilted at some angle because x plus 2y plus 3z is a complicated expression. And we want the part of this above the plane. All right. So typical cut looks like that. The question is, where exactly does the xy plane live relative to this picture, right? If the xy plane lives down here, then our region is going to look something like this. All right. If our xy plane lives all the way up here, right, relative to the other two guys, then our picture is going to have to be cut. So it'll be like one of the examples we did last time. So let's figure that out first so that we get a good view of our region, and then we'll be able to set up the integral. Okay, so let's look at it in this way. So to determine where the plane, so x plus 2y plus 3z equals 6, where does it hit the xy plane, right? So this is what we essentially want to find out, because if we look from above, here's our cylinder, right, of radius 1. If our plane x plus 2y plus 3z hits the xy plane something like that, right, then again, like we said, our region of integration is going to be something like this. However, if it doesn't touch the circle, right, like that, then we'll have a picture like this one above. Okay, so we want to know the relationship between this plane and the xy plane. Okay, all right, so where does it hit the xy plane? That's going to be where this equation and the equation for the xy plane is satisfied. The equation for the xy plane is just z equals 0, right? So we're considering, in effect, the line x plus 2y equals 6. And the question is, does this hit the circle of radius 1 about the origin? Okay. All right, in terms of the picture, x plus 2y equals 6. When y is equal to 0, we have x equals 6. And when x is 0, y is equal to 3. All right. So it's not going to hit, but let's make sure. So let's make sure using Lagrange multipliers, right? There's lots of ways we can actually make sure, but since we just learned Lagrange multipliers, let's do it that way, right? So what we're going to do is we're going to figure out what is the minimum distance from our line to the origin. All right, and if the minimum distance from our line to the origin is bigger than 1, then our picture has to look like that, right? If the minimum distance is less than 1, then that means our picture has to look like something like that. Okay, so this completely is going to answer the question that we want. So minimum distance, this is why it's a Lagrange multiplier problem, right? This is why it's an optimization problem. It's a Lagrange multiplier problem because we have a constraint. We're only interested in points on this particular line, all right? So we'll quickly solve this. As usual, when we work with distance, it's easier to work with the distance squared function just for computational purposes. So let's try to find the minimum of this capital D function equals x squared plus y squared. So minimize subject to x plus 2y equals 6. All right. So I'm going to need to create a function that has a level curve equal to this guy here. And so that's going to be, let's use gxy equals x plus 2y. And then our line is going to be, so line is 6 level curve. All right. Okay, gradient capital D is 2x comma 2y. Gradient G is 1 comma 2, right? Gradient D equals lambda gradient G becomes 2x equals lambda, 2y equals 2 lambda, right? And of course, if we want to write out everything completely, we also have x plus 2y equals 6, right? We need to be on the line. We're only interested in points on the line. Okay, so again, we do this algebra differently depending on what the structure of our equations are. But for this particular problem, it looks like if I look at the first two equations, I'm going to get, since lambda is 2x and 2 lambda is 2y, we get 2x, sorry, let me write it like this. 2y is equal to 2 times 2x, right? Which tells me y is equal to 2x. Okay, since y is equal to 2x, so notice I didn't do any cancellation of lambda or anything like that. I just substituted lambda equals 2x into the second equation. So there's nothing to worry about in terms of having done any illegal cancellations or uncareful cancellations. All right, y equals 2x. So this tells me, plugged into the third equation, tells me x plus 4x is equal to 6, which tells me 5x is equal to 6, which tells me x is equal to 6 over 5, which tells me y is equal to, well, y is equal to 2x. So if x is 6 over 5, y is equal to 12 over 5. All right, so the point that's close as possible to the origin on our line is 6/5, 12/5. Okay, distance to origin or distance squared, let's say, is 36 over 25 plus 144 over 25, which is 180 over 25, right? That's definitely bigger than 1. And so that means that if the closest point on our line to the origin is bigger than 1, that means our line cannot touch the circle of radius 1. Okay, so our picture does indeed look like something like that. Okay, which means our 3D picture does indeed look something like, I don't need the axis, I just want to kind of have a picture of the solid. So it does indeed look like that. Okay, all right, knowing that it does look like that tells me that I want to do integrals from the ground with respect to z all the way up until I hit the plane, right? So when I do my integral, I'm going to do dz, z equals 0 to z equals the plane. Our plane was x plus 2y plus 3z equals 6, right? So this was x plus 2y plus 3z equals 6, which tells me that this equation should be 6 minus x minus 2y all over 3. Okay. All right. So the outer two integrals, so we're working in cylindrical coordinates. So the outer two integrals are going to be in terms of r and theta. And we can see that this is really nice for us because we're integrating just over a circle of radius 1, right? This is actually our the shadow of our region. And so that's super simple. R equals 0 to our radius. And then theta equals, we want the entire circle, so 0 to 2 pi. And of course, when we integrate dr d theta, we have to have an r dr d theta. We wanted the volume, so this is all we need. All right. Okay, so a nice combo problem. We didn't necessarily have to use Lagrange multipliers to figure out the location of this line. But again, it's a nice application of some of the stuff that we've learned. Okay, what happens if the plane did intersect a cylinder, right? What if, for example, let's change the plane to x plus y. Let's do a relatively simple one. 3z equals 1, right? So in this particular situation, this plane is going to intersect the xy plane within our circle of radius 1. All right. So if I draw the xy plane, kind of the xy plane picture, here's our cylinder of radius 1. We can easily see this because when y and z are 0, x is 1. And when x and z are 0, y is 1. And so our plane actually cuts the xy plane right there. All right. Okay. Of course, this plane, if we extended the picture, it would look like this. Just to make sure, the portion that's above the xy plane is the portion that's on this side, right? And the portion that's below the xy plane is the portion that's on the other side. That's not the side we want, right? We want the region below the plane above the xy plane, right? How do we know that? Well, for example, a quick check, right, tells me, or a quick look tells me if x and y are both positive and really big, then in order to add it to 3z and get 1, z has to be negative, right? And so out here, z has to be negative, right? But knowing that out here it has to be negative, or I guess I was doing here, knowing that z is out here very far away, just at one point, knowing that's negative, well, because it's a plane, right? If it's negative at one point here, it has to be negative for the entire side. Okay, that's just one way to do this analysis. All right, so in any case, as it turns out, we want, again, the region below the plane above the xy plane. So the region that we actually want to integrate over is this portion right there. Okay. All right, so how would we do this if we wanted to do it in terms of cylindrical coordinates? Well, one way is the way is, let's set it up, triple integral. Our inner integral, the dz, right? We're doing the volume, so we're just integrating one, right? The innermost integral is still the same idea, right? Our picture is a little different this time. It looks something like this, right? Very much like the wedge that we did in a previous section. But this top part is a plane, right? So we're still integrating from the ground to the same plane, or our new plane, right? So this is still going to be z equals 0, the ground, to z equals the plane, which in this example, because our plane is x plus y plus 3z equals 1, it's going to be 1 minus x minus y over 3. Okay, so the interesting portion of this problem is the dr d theta, right? So dr d theta, and then of course if we have a dr d theta, we're going to have to pop out an r, right? So the interesting part here is we can see the r is going to be different. Our rays through the emanating from the origin are going to be different depending on which direction we're pointing, right? So rays through the origin, or rays emanating from the origin, let's say down here, go all the way to the circle, right? To the circle, to the circle, to the circle, to the circle. So when we're doing our dr integral here, it's always going to be from the origin all the way out until we hit the circle. Okay. However, if we're over here, we're not going all the way to the circle. We're going until we hit the line. All right. So it looks like we're going to have to, well, we are going to have to break this up into two different integrals. The easier one is the one that goes from 0 to the circle. So let's write that one first. This is r equals 0 to r equals the circle, which was circle radius 1. But we're not doing the entire 0 to 2 pi. We're doing, for example, we could write it as pi over 2 to 2 pi. Okay. All right, so that covers everything except this first quadrant portion of our integral. The first quadrant portion is going to have to be, let's see, so we're doing r d z d r d theta, z equals 0 still, to z equals 1 minus x minus y over 3. And now the question is, r goes from what to what? So let me draw the picture again. So just this portion here, we're going from r equals 0 to the line, r equals 0 to the line, all right? So r equals 0 to the line. Now, what is the line? The plane was x plus y plus 3z is equal to 1. This line is defined by where that plane hits the xy plane, so the z is 0. So the line was x plus y equals 1, right? If we write that into polar coordinates, that's going to be r cos theta plus r sine theta is equal to 1, which means r is equal to 1 over cos theta plus sine theta. And we know we want to write it in terms of r equals something, because we know this second integral here should be r equals something to r equals something, all right? So in particular, this r equal line should actually be r equals 1 over cos theta plus sine theta. Okay. All right. And a theta is going to be straightforward. We want these rays starting from the very first one here, theta equals 0, and we need to fill up this entire region with rays until we get to theta is pi over 2. So theta equals 0, theta equals pi over 2. Okay. So altogether, it looks like if we did want to do this with, insist on doing it with cylindrical coordinates, we're going to have to break it up into two integrals. Looks like it possibly could be a bit of a mess because of this this r equals 1 over cos theta plus sine theta. So in practice, one thing you can consider is actually doing just the first portion in cylindrical coordinates, just as we did. But the second portion, because it looks like a triangular region, maybe doing it with rectangular coordinates might be easier. All right. So always keep that in mind. You don't have to do the entire problem using just one particular technique. Okay, so that's the kind of region kind of considerations in terms of when you want to use cylindrical coordinates. In terms of kind of what you're integrating, if you have functions which look like a cone, right? So f of x comma y. Let's say you want to find the volume under. Sorry. Let's say you want to find the volume of a inside a cone or something like that. Or remember our ice cream cone problem, right? We wanted the volume underneath a sphere, but above a cone. So that could be well suited for cylindrical coordinates because, well, like as we said, or as we calculated when we did this example, the shadow in the xy plane was a circle, right? And that's, again, well suited to cylindrical type coordinates. Also, anytime you work with cones, right, cones can be very easily described in cylindrical coordinates. They're just z equals a constant times r, right? So the kind of typical 45-degree cone, for example, is z equals square root x squared plus y squared, right? We've seen this many times. But square root x squared plus y squared is just r, right? And so so if you put a constant in front of that r, you're going to get cones of different different widths, right? So if z is equal to something big times r, z equals 100r, you're going to get a very sharp cone like this. And if z is equal to 1/10 r, you're going to get a very flat cone like this. Okay, so the equation for a cone is very simple in terms of polar or slash cylindrical coordinates. All right, other situations, paraboloids, right? So if you see something like z equals x squared plus y squared, or perhaps in the form x squared plus y squared minus z equals 0, same idea, right? That guy here is your r squared, right? And so the paraboloid can be described just as z equals r squared. Nice and simple. Okay. The sphere, z equals square root, for example, radius 3, 9 minus r squared. Okay, so a little bit more simple than using rectangular coordinates. So keep in mind, when you do have integration problems that involve things like x squared plus y squared, which all of these examples do, if you convert that to r, things might be a little easier. Okay, one more comment. The way we typically use cylindrical coordinates is r and theta represent your position. Again, if you have a point, right, in space, what cylindrical coordinates does for you is it represents that point using 3 bits of information. The first bit is that r right there, that theta right there, right angle from the positive x-axis, and then this height right there as z. Okay, let me leave it like this. Okay. However, one thing you can always keep in mind is the z is kind of arbitrary. Perhaps there's situations where you might want to do r theta, have r theta representing the, so this is x, y, z, x, y, z. Perhaps the y and z plane, right? And then you're pulling out things towards the x-axis. And then perhaps you would describe things, like this, where this is your theta, that's your r, right? And then your height would be x. Okay, so then maybe r theta x, where these two represent a position in yz plane. I'm going to put that in quotes. That's not completely precise, right? Maybe more precise would be position of the shadow of this object on the yz plane. Just as that blue point right there is represented by r theta, right? That's a position in the XY plane of the shadow of the actual point that we're looking at. Okay, by the way, one way to describe r in words, maybe a good thing to keep in mind, is r is the distance from, well, you can say it's from distance from the origin to the shadow, but also it's the distance from your point to the z-axis. All right. Okay, so keep in mind that you might want to do cylindrical coordinates maybe based upon a plane other than the xy plane. Okay, next, spherical coordinates. So this is a lot more new. And it's an extension, again, of polar coordinates into 3D, into space, except with cylindrical coordinates, we did the kind of really simple thing of just extending into space by adding a height direction. Spherical coordinates, you're describing things a little differently. You're using, so if you have a point right here, right, this is our point of interest. Let's say this is the shadow on the xy plane. So in polar coordinates, we used r and theta, right? R described how far you were from the origin, and theta described kind of your, in a way, your position on this unit circle, right? So let me draw that. In the polar coordinates, you have a point right there, right? R and theta. R describes distance to the origin. Theta describes where you are, right, along the, around the unit circle. Okay, so when you extend that idea, kind of stated that way, to spherical coordinates, then one thing you can say is, okay, I want my new coordinate system to describe how far I am from the origin, right? So we're going to use rho for that. Let me. All right, so the Greek letter rho. That's how far you are from the origin, right? So that is our analog in spherical coordinates to the r in polar coordinates. Okay, now the other two coordinates are going to represent where you are in terms of the sphere, right? Just like theta tells you where you are in terms of the unit circle. Okay. All right. So how do we do that? Well, we're just going to borrow from polar coordinates. We're going to use the same theta as in polar coordinates. All right. So if this is our point, we drop the shadow down to the xy plane. We can look at the angle that this shadow makes with the x-axis, positive x-axis, and we're going to use that as our theta. Okay. So that's going to be our second coordinate. All right. So this doesn't really describe the kind of third dimensional property, and that's kind of how tilted this point is from the z-axis. And so our third coordinate, let me make this a little smaller. Let me call that equals rho. All right. Our third one is going to be the angle that our point makes with the positive z-axis. So it's going to be that angle right there. All right. So this is going to be phi. Okay. So if you do have all three of these, you can describe exactly, precisely where you are in space. And again, the rho describes how far you are from the origin, and the theta and the phi describe where you are, kind of your which direction you're in, right? Okay. In fact, if you think about this, let's draw a sphere. Oops. Here's the origin. Here's the equator, for example, right? So if, for example, here's, let's say, the positive x-axis. Okay, so if theta were fixed, let's say that angle right there, that's theta, right? What would that describe on a sphere? for theta fixed? Well, it would describe a great circle like that, right? If theta were fixed at a different angle, it would describe another great circle, right? They would all touch up at the North Pole and the South Pole, something like that. Okay, so phi is longitude. Oh, sorry, theta is longitude. Theta is longitude, right? So when you think about maps, this is exactly what longitude is. All right, so theta is longitude, essentially. Okay. All right, what about phi? Well, phi describes your angle from the vertical. So constant phi would be something, I'm going to do this in a new picture. So constant phi would be, for example, a constant angle here. And if I think about all the points on a sphere with this particular constant angle, it's going to cut a circle like that, right? A different one would cut a different circle at a different kind of height. Okay. And so that's actually latitude. Okay. All right. At least latitude in spirit, right? I think in real life we describe latitudes where the equator is 0 latitude, but in spherical coordinates, we're describing angle from the z-axis. And so the equator would be actually phi equals pi over 2. So be kind of aware of that. Okay, so again, in short, these two guys describe where you are on the sphere. The rotate tells you how far out you are, which spherical shell you're kind of at. Okay. All right. What about the ranges of these quantities? Well, rho should be, rho generally, we're going to have it be bigger than 0, bigger than or equal to 0, right? You can technically have rho negative, just like you can technically have r negative in polar coordinates, which means you're pointing in the opposite direction. But generally, we like to have phi be non-negative. Theta, we're used to working with theta between 0 and 2 pi, so let's leave that. Okay. But if you do have these two, then phi is only going to range from 0 to, or phi only needs to range from 0 to pi. All right. That will cover everything. So if you think about the longitude and latitude situation, right? If you do have 0 to 2 pi, describing your longitude position, for example, we're right here, right? Then the only question is where you are from here to there. Okay, because the opposite side of this circle, we could describe using 180 degree or pi shift in theta. All right, so traditionally we only use phi from 0 to pi. Okay, this is a really good way to extend the idea of polar coordinates because this also extends to higher dimensions. So if you want to work in 4 dimensions, a good way to do it is you have one variable representing distance from the origin, and then you use 3 variables to represent kind of your angle in a way, right? Your position on a 3-dimensional unit sphere, for example. All right, conversion. So in our class especially, we often have problems that are given in terms of rectangular coordinates. So how would we convert rectangular to spherical or vice versa? Okay, so the way we figure that out is we just draw the picture. So again, we have a point here that we're interested in. this is a right angle right there, all right? Because this is this point down here is the shadow of our actual point, our shadow on the xy plane. All right, so this is what we're calling phi, right? Phi equals 0 would be pointing straight up, right? Phi equals pi would be pointing straight down. Okay, this guy right here is theta, and then the length of this segment up here is our rho. Okay, to figure out our conversion, it's probably very most convenient to actually write down r as well here, right? R again is distance from here to the shadow, right? Or again, distance from here to the z-axis. Okay, so what we have is, let me put this row over here. What we have here is a right triangle, right? This blue triangle right here is a right triangle because down here we have a right angle. If this angle here is theta, then that angle right there is also theta. All right. Okay. We know r and phi, so r over phi, so r over rho, let me write it like this. Sine of phi is equal to opposite over hypotenuse. Okay. All right, so this allows me to convert, right? So, so r is equal to rho sine phi. Okay. So this actually allows me to switch between polar coordinates or cylindrical coordinates and spherical coordinates. All right, but what about x and y? Well, if r is equal to rho sine phi and x is equal to r cos theta, right, just from our use of polar coordinates, that means that x should be equal to rho sine phi cosine theta. Okay, so that's our conversion. Okay, from polar coordinates, we know y is equal to r sine theta. And so if r is rho sine phi, this is rho sine phi sine theta. All right. Okay, again, these are slightly nasty looking formulas, but you can always reproduce them very, very quickly if you need them through this picture that we have above. Okay, what about z? Well, we go back up here. If we draw this dotted line here, right, we have this height is z, and we have a right triangle right there. Oops. We have a right triangle right there. Rho is the hypotenuse, and so what we see is that adjacent over hypotenuse, so cosine of phi is equal to z over rho. Adjacent over hypotenuse is the cosine. Okay, and so immediately z is equal to rho cos phi. All right, so that allows us to convert from xyz to spherical coordinates, which is mostly the type of conversion that we are going to be doing. If you do want to convert in the other direction, it's relatively straightforward, right? Because we know rho squared is the distance to the origin, so x squared plus y squared plus z squared, right? And so rho is going to be square root of that. Theta is the same theta from polar coordinates, so it's just arctangent y over x. And again, if you can't remember this, you can always reproduce it from trig, right? And finally, let's see. We know z equals rho cos phi. So if we want to convert phi, well, cos phi is equal to z over rho, which is z over square root x squared plus y squared plus z squared. And then you can take your arc cosine on both sides. All right. Okay, one nice observation here is if you look at our three formulas for x, for y, and for z, um, if you take x squared plus y squared plus z squared, the right-hand sides of these, you should pop out rho squared, right? So let's just do this is kind of, maybe you think of this as a quick check of our the three formulas that we got above. Okay, so if x is equal to, so x squared plus y squared plus z squared is equal to, x was rho sine phi cos theta, right? So this whole thing squared. And then y was rho sine phi sine theta. And then z was rho cos phi, right? So if we actually compute this out, let's see, we've got rho squares all the way through. We've got a sine squared phi cosine squared phi theta. We've got a, let me just pull that rho out. We've got a sine squared phi sine squared theta, and we've got a cosine squared phi. Okay, so here we've got a sine phi, and then a cos squared plus sine squared. So that just turns out to be cos squared theta, or cos squared phi, sine squared phi, right? Because cos squared plus sine squared is 1, and then cos squared phi. And so we just end up with rho squared, which is correct, right? X squared plus y squared plus z squared is distance to the origin squared. Okay, what are spherical coordinates good for? So they're great for working with spheres. Of course, because what is a sphere of radius 9, right? X squared plus y squared plus z squared equals 9. That's just rho squared equals 9, which is rho equals 3. So super, super simple compared to the rectangular coordinate version of the equation. And even the cylindrical coordinate, right? That would have been r squared plus z squared equals 9. Significantly more complicated than rho equals 3. Okay, so that's kind of obvious, but maybe less obvious is great for spheres, great for cones, centered, let's say with vertex, or let me say it like this: centered about the z-axis. All right. So what I mean is a picture like this, a cone like that, right? So just as polar coordinates were good with these things. Remember, it was just z equals a constant times r, right? The constant telling you how fat the cone is. Spherical coordinates is actually even better, because what is this cone? It just describes a constant phi. All right, so phi equals a constant, and of course that constant is just whatever angle this guy is. All right, so our kind of typical, in a way, cone of z equals square root x squared plus y squared would just convert to being phi equals pi over 4. Okay, so this left-hand side is pretty nasty, right? When you're doing integrals, you don't really want to see this, because oftentimes that square root is going to give you huge trouble. But in spherical coordinates, it's just described using phi equals a constant. Okay, what is theta equals constant in terms of the picture? Well, that's going to be where you have x, y, z, where you have a constant angle with the x-axis. And what are the things with the constant angle with the x-axis? It's going to be like a planar region, right? Planar region perpendicular to, of course it extends perpendicular to the xy plane, all right? Okay, technically this planar region would only be on kind of this front-facing side, not the back, because phi only goes from 0. So phi would only go from 0, which would this angle, all the way down to that angle. So we're not getting anything kind of in the back, all right? The other side of the plane. So it's technically a half plane, I guess. All right, so so far so good. What we're really interested in this chapter is integration. So the question is, how do we actually integrate um, in terms of spherical coordinates? So triple integral dv f over region, right? So we already said in rectangular coordinates, it's just d whatever dz dy dx, right? Straightforward. In polar coordinates, r dz dr, sorry, r dz, yeah, dr d theta. All right, and then we got our f. So now what is the question is what should it be in spherical coordinates? When we introduced polar coordinates or integration in polar coordinates, we kind of figured out why the r had to be there, and that was because as we go further out, right, the wedges actually depend, how big each wedge is depends on r. So you're going to have that r factor in there if you're going to get your kind of volumes or your areas correct. So what about in spherical coordinate? Well, you can do exactly the same idea, except instead of kind of just a small wedge like this, a two-dimensional wedge, you do the analysis with like a three-dimensional wedge, right, like that, where the origin is out here. And again, the size of these wedges get bigger and bigger as you go further and further out away from the origin. All right. Okay, so you can do the analysis, and as it turns out, if you want to do a integral in terms of spherical coordinates, you're going to get d rho, d phi, d theta, for example. This is probably the most common order of integration that we'll see in our class. We're going to restrict ourselves to relatively simple three integration in spherical coordinates. So this will be by far the most common order of integration. So what's the factor out in front that's equivalent to this r out here? Well, it's rho squared sine phi. All right, and then of course you have whatever f you have you're integrating over, and your limits of integration. Okay. Okay. The sine phi needs to be there because the way we use because when we have theta, right? Let me draw a small picture here. Near the North Pole, right? It's very easy to move a large amount of theta compared to near the equator, right? And so phi kind of determines how far you are, right? Whether you're near the North Pole or you're near the equator, because it's the tilt from the z-axis. And so because of this, there needs to be a sine phi to kind of compensate for this. Okay. I'm not going to do the derivation because, so for this chapter, I guess, or for this section, you're just going to have to believe me on this. But next section will tell us exactly why. Next section, we're going to do a general situation where we can figure out kind of what factor should be in front of coordinates if we do any kind of crazy coordinates, not just cylindrical, not just spherical. All right, so we'll talk about that next section. But if you do want to, you could figure out yourself, kind of always keeping in mind how we did it with polar coordinates, and then try to do it in an analogous way. Okay, so let's use this. So let's start with the most simple example. What is the volume of a sphere of radius capital R about the origin? Or actually, we don't have to say about the origin. Sphere of radius capital R. But about the origin means that if we do this in spherical coordinates, it's going to be nice and simple. So we already did this with polar coordinates, and it was relatively simple. But in spherical coordinates, it's going to be super simple. So we have a triple integral. we're doing this in spherical, so so let me write, oops. We're integrating, we want the volume, so it's just 1, right? And then rho squared sine phi. 1 is the function we want to integrate. And then d rho, d phi, d theta. Again, this is typically going to be the ordering we want. What are the limits of integration? So for spherical coordinates, our d rho integral, if we want to draw a picture like the lines from rectangular coordinates or whatever, our rho integral is going to be represented by rays that come from the origin. All right, very similar to in polar coordinates, right? Our dr integral were represented by rays from the origin. Okay, so and that makes sense because rho describes distance from the origin, and if you have rho moving but theta and phi fixed, then that's exactly a ray coming out from the origin. Okay. All right. So remember that if you integrate with a with respect to a coordinate as the inner integral, you just look at the integral is represented by that coordinate changing, whereas when all the other coordinates are fixed. All right. So again, when rho is changing and the other coordinates are fixed, we're talking about rays through the origin. Rays through the origin. Okay, or rays emanating from the origin. Okay, and we're integrating over a sphere of radius r. So when we do want to fill this region up with rays emanating from the origin, right, we can see we always start with a ray at rho equals 0, at position rho equals 0, and we end up at rho equals capital R, which is the surface of the sphere. Okay. All right. What about the other two? So the other two, normally we think of it in terms of a shadow, right? In rectangular coordinates, if we do dz first, we think about the sun shining from above along the z-axis, and then down, our object creates a shadow in the xy plane. Okay, so now what's happening is one way you can think of this is we have a sun or a light bulb or whatever, a sun shining at the origin. Okay, and typically we want to think of a kind of an abstract, gigantic sphere out here, right? Super, super far away from the origin so that our surface kind of, or our region doesn't interfere with it. And the region that we want to integrate is a region on the sphere because it's described by d theta, d phi. What region on the sphere? Well, the region that is shadowed by our object when the sun shines from the origin. Okay. All right, so in this particular example, if we do have the sun shining from the origin, our object, which is this sphere, completely blocks out all light. And so on this big abstract sphere out here, everything is shadowed, right? So that means what we want to integrate over is the entire, entire sphere. Okay. All right, what is the entire sphere? Well, that would be phi from, the entire range. So phi from 0 to pi, and theta from 0 to 2 pi, right? Okay, if you do want to think of each of these integrals, these two integrals individually, the phi integral would represent integrating like that, right, along a kind of a half great circle between the north and south poles. So this would be one particular integral, this would be another one, this would be another one, and so on. And then we want, which of these great circles do we want? Well, we want to fill up the entire sphere with these great circles, or half great circles. And so we need theta to be 0 to 2 pi. Okay. All right, So let's actually do this particular one just to see, again, the formula for the volume of a sphere pop out. Okay, so this is going to be 1/3 rho cubed sine phi evaluated from rho equals 0 to capital R d phi d theta. And so we have 1/3, let's pull that out, theta equals 0 to 2 pi, r cubed. Let's pull out the r cubed as well. Integral of sine is minus cosine. We're evaluating that from 0 to pi, and then d theta. Okay, so that's going to be r cubed over 3. This quantity in here is going to be cosine pi minus cosine 0 is going to give me minus 2, but I have a minus sign in front of it. So I'm going to have 0 to 2 pi of just a constant 2. And so I end up with 2 pi times, let me write it all out, r cubed over 3 times 2 pi, right, as our d theta integral. And so we get our usual formula, 4 pi r cubed, 4/3 pi r cubed. All right. Okay, let's do a more interesting example. Let's integrate, let's say, let me just make up a function, x, y, z equals xy over the region, over the solid. That's inside the sphere and above, or sphere of radius, let's say 2, and above the cone z equals let's say 3 square root x squared plus y squared. Okay. All right, so this is going to be ice cream cone. Right, so this is our cone, and then we've got a sphere like that. Okay, so this is perfectly suited to integration using polar coordinates, because at least in terms of the limits of integration and stuff, because if we do, let's see, xy rho squared sine phi, let's do d rho first. So the d rho integral is rays through the origin. So we can see we start a ray here, and we always come out until we hit the sphere, right? Always from here, hit the sphere. Always from here, hit the sphere. So we know we can do this just with one integral. And it's always rho equals the origin to rho equals the sphere. It's a sphere of radius 2, so just 2. Okay. I guess to be most precise, I should be a little careful here. Sphere of radius 2 about the origin. Okay. All right, d rho. So what about d phi d theta? Well, the d theta is often going to be, at least in the problems that we'll be seeing, very straightforward. We want to integrate the entire range of theta, right? Because this is the entire ice cream cone all the way around. Okay, so theta is going to be 0 to 2 pi. Okay, what about phi? Well, if I just draw this ice cream cone in terms of, let's say, r and z, right? Or we can just use x, but maybe r is a little more precise here. Then the ice cream cone is going to look something like this. All right. Okay, this is a sphere of radius 2. Maybe I should do that here. And this guy here is, well, z equals 3 square root of r squared. So this is z equals 3r. Okay. All right, what that means is z equals 3r is a line, right? So if we move one step to the right, we're going to be moving 3 steps up. All right, let me just write it like this: slope 3. Okay, line slope slope 3. Okay, let me just draw it by itself. So 1 step here, 3 steps up. All right. Why do I care? Well, if this is the z direction, that's the angle that I want, which is the same as this angle right here. Oops, sorry about this. Right, which is the angle right there. And opposite over adjacent, tangent phi is opposite over adjacent. And so phi is equal to arctangent 1/3. All right. So that describes the boundary of the cone, right? And what we want to do is we want to integrate the entire region inside. So we want to integrate from here to here to here to here to here, all the way to the edge. So that would be from phi equals 0, oops, to phi equals arctangent 1/3. And again, it looks kind of terrible, but arctangent 1/3 is just a number, right? So this these 3 integrals here, just constants. The limits of integrations are just constants. So that's really great. And it's a great feature of using spherical coordinates. However, of course, you're going to have to convert this x and y into spherical coordinates if you want to do the integral, because our integral should be in terms of what happened there, in terms of rho, phi, and theta, right? So you're going to have to convert the x. X equals rho sine phi cos theta, and y is rho sine phi sine theta. All right. Okay. In terms of the shadow idea, right? If you wanted to figure this out, kind of looking at shadows, this region here. So we had our ice cream cone like this, right? We're doing our rays through the origin like this, right? Rays from the origin as our rho integral. If we have kind of a big abstract sphere out here, where is the shadows going to be? Well, oops, the shadow is going to be determined by the cone, right? And we're going to end up with kind of the cap portion of a sphere. I guess I shouldn't fill it in like this. A cap portion of a sphere here, right? So this cap portion is exactly what we described using theta equals 0 to 2 pi and phi equals 0 to arctangent 1/3. Okay. All right. Maybe as another example of this of the shadow idea, if we were integrating, let's say, for whatever reason, we want to integrate the region inside this cylinder using spherical coordinates, then we would have to integrate from here until we hit the cylinder, until we hit the cylinder, until we hit the cylinder, right? And then there would be another portion where we hit whatever's up here, the cap, right? If it's a flat plane, then z equals a constant, right? Z equals a constant. So we would have to actually break this up into multiple pieces. But in terms of our shadows, right? In terms of the phi and the theta integrals, then the portion of the integrals, which is to the cylinder, we're going to have to integrate everything from here all the way up to there, all the way up to there, right? So we're going to, the shadow, if we put the sun right here, right, and it's shining just on the cylindrical part, then the shadow is going to be everything except a chunk of a cap on the sphere, right? And then when we do the top part, perhaps, then we'll fill in that cap in the other integral, all right? So if you are working with more complicated regions, the sun shining its shadow on a sphere in order to get the phi and theta integrals, limits of integration can be very useful. All right, if for whatever reason you're doing a different order of integration, let's say you do d theta first, then you would be representing your integrals. The d theta integral would be represented by circles like that, right? So this circle here is at a particular, distance, right, to the origin, and it's at a particular angle. So those two things are fixed, only theta is changing. And what that looks like is just a circle. Okay. All right, what would the shadow of this be? The shadow would be, so your other two coordinates are rho and phi. What does that describe? That these two guys, just those two guys together, describes a plane, right? So perhaps you could use as your shadow this plane right there, right? So the the YZ plane, right? And the areas that would be shadowed would be the ones that are blocked by this circular, in this case, it would have to be like a circular ray of light, right? And if it hits your region, then that means there's a shadow on your plane, and that means you need to consider it in terms of your phi and rho integral, all right? So this is, of course, this is super rare. You're almost never going to integrate with respect to d theta first, but it's good to think about this just to, if you think about this, maybe it'll help you understand the shadows for the d rho first situation, right? Okay, in the same way, if you want to integrate with respect to the, so let me write this first. If you want to integrate with respect to the d phi first, that would be represented by, again, theta would be fixed, right? And rho would be fixed, your distance to the origin would be fixed. And so you would be integrating over kind of circular arcs like this, all the way down to the other side. This looks a little weird. So circular arcs all the way down to the other side. All right. Okay, and then what would your shadow be? In this case, perhaps you can use the XY plane as your shadow, and your sun would be shining in a way in arcs from the z-axis, and anything, as usual, that's blocked by this by the sun, right, shining along these arcs, would create a shadow here, right? And those are the regions you have to integrate over for your rho and your theta.